Okay, in our last recorded lecture, we discussed about what is dynamics, how we can differentiate between the kinematics and kinetics. We discussed the difference between the particle and the rigid body. After that, we briefly learned about the rectilinear motion, and after that we started the curvilinear motion. And in that topic we discussed that if our particle is moving in a curved path, then its motion can be defined in three different coordinate system based on the available data and the given scenario. So the three coordinate systems in which the motion of the particle can be defined are: number one is rectangular coordinate system, the other one is the normal and tangential coordinate system, and the third one is the cylindrical coordinate system. So how we can define the motion of a particle in a curved path by a rectangular coordinate system? We have also covered this topic. Now we are going to discuss that how this motion can also be represented in a normal tangential coordinate system. So let's move ahead and go into the further detail of this topic. Before starting the normal and tangential coordinate system, let's have a recap that what we have studied in the rectangular coordinate system. So, as our particle is moving in a curved path, so we can define its velocity, its position, and acceleration in three different coordinate axes, which is x, y, and z. So as this curve path, which is the simplest circular curve path, and it is in a plane, so this is a 2D curve. So we can explain its position, velocity, and acceleration in terms of only two coordinate axes, which is x and y. So let us draw the coordinate axis. This is our y and this is our x, right? So let's start that when t is equals to 0, the position of our particle is over here. So this is our particle, right? So we can represent its position from the reference point or the origin, and can say that this is the position vector r1, and at this instant the position can be defined as x1 and y1. Similarly, this particle move from here to there. So when it comes over here, then we can say that after when t is equals when t is equals to 1, so its position can be defined as x2 and y2. So this is the position vector r2, this is r1. Similarly, at this point it has only one component of the velocity, which is v1, and it is only in x direction. Similarly, when it reaches over here, the velocity vector will be tangent to that point and can be resolved into x and y axis. So this is v2 and can be represented as vx and vy, right, which can be obtained from the differentiation of the position vectors. So this was the case when we deal with the motion of a particle in a curved path by a rectangular coordinate system. In this coordinate system, we defined our position, velocity and acceleration in terms of x, y and z axis. Now, based on the given scenario and the available data, we can also define the motion of a particle in a curved path by a normal and tangential coordinate system. Okay, we have a similar case in which we have a particle which is being attached with a string and it is moving in this circular path, right, with some constant angular velocity of 60 rpm. So as long as this string is okay, then this particle will continue to swing in this circular path. For suppose the radius of this path is 3 meters. Okay, for suppose when the particle is over here, then the string break. Now what will happen? Then we will see that the particle will move in this direction, or it will move in this straight line, So now my question over here is that with what velocity it will move in this direction. So as an answer, we have to calculate this linear velocity. As we know that the velocity is in meter per second, so we have to convert this angular velocity into this linear velocity. So what we will do? We will we know that this is 60 rpm, so revolutions per minute. So we multiply it for revolutions. It covers the circumference. So this is 60 multiplied by 2 pi r divided by 60, right? The radius is 3 meters. So when you convert it, when you solve it, you will get 18.8 meters per second. So this is the velocity by which it will move in this straight line, right? Now for suppose if our particle is over here and this string break, then of course it will move over here. Now with what velocity it will move in this direction, right? So as we have same radius and constant angular velocity, so we will have the same velocity, which is 18.8 meters per second. Now my question is that is the speed changing? So as the particle is moving in circular path, is its speed changing? So the speed is not changing because the particle is moving with the constant angular velocity. So the speed is not changing and it will remain 18.88 anywhere on this path, right? Now my question is that is the velocity changing? So the answer is yes, velocity is changing because the magnitude hasn't changed, but the direction is changing everywhere. So that is why the particle is moving in this circular path have a different velocity due to the change in its direction. So now, as per the definition of the acceleration, that acceleration is the rate of change of velocity, that is why we have also the acceleration of the particle moving in this circular path, right? Now, in order to define the acceleration of the particle moving in this curved path, let's introduce a new coordinate system, which is normal and tangential coordinate system. So in this system, we have a tangential direction which is always tangent to the path. So that is why uh, we call this we call it a tangential axis, and represented by the unit vector ut, right? And the axis which is perpendicular to that axis is called the normal axis, which is always directed towards the center, and it called as normal axis and represented by unit vector un, right? So as we have discussed that the particle moving on a curved path will have only one component of the velocity, which is the tangential direction, right? So we can say that the particle moving in the curved path have only one component of the velocity, which is actually vt, and this will always tangent to that path or tangent to that point. And we also have discussed that the particle moving in the curved path have the acceleration due to the change in the direction of the velocity. So that is why we have two components of the acceleration of the particle moving in a curved path. Number one is called the tangential component of the acceleration, and the other one is the normal component of the acceleration. So as you have learned that the particle has only one component of the velocity, which is vt, and you have observed that the magnitude is not changing with respect to time, rather only direction is changing. That is why the tangential component of the acceleration is 0 over here, because the magnitude has not changed. But we have a normal component of the acceleration, which is due to the change in the direction of the velocity, which is calculated by v square upon rho, where rho is the radius of curvature, right? So in order to calculate the acceleration, we can calculate the resultant by a is equals to at square plus a n square. So, what is the summary? Summary is that the particle moving in a curved path can be represented by a normal tangential coordinate system. In this system, we have two axes. One is tangential axis and the normal axis. Tangential axis will be always tangent to the point on the curve, and normal axis is always directed toward the center of the circle. The particle has only one component of the velocity, which is the tangential component, and it has the two component of the acceleration. One is tangential and the other one is the normal. So tangential component will be due to the change in magnitude, whereas the normal component of the acceleration will due to the change in direction, right? Now, this is not always the case in which the circular path is given to you, and you can calculate the radius of curvature, which is rho in this case, for calculating the normal component of the velocity, right? So you can also given with some other curve path by on which you have to calculate the acceleration or the velocity. So how you will calculate the radius of curvature in such curves? So basically, when this type of curve is given to you, we can uh, distribute this curve into little segments, right? Like over here, and each segment on this curve will represent the uh, arc of a circle. For suppose if this is the arc, then it will cover this whole circle, right, which has the radius of curvature over here. Similarly, For suppose if I am considering this arc, then it will be the arc of a circle which is over here. So we can say that this curve is composed of different arcs which will be the part of a greater circle having the radius of curvature rho. So if the function of this curve is given to you, then you can easily calculate the radius of curvature at any point in this curve by using the relation which is rho is equals to 1 plus dy by dx square power half divided by d square y by dx square, right? So if the curve is given to you and the function is given, so you can calculate the radius of curvature anywhere on this curve path by using this relation. So over here I am not going into details that how this equation can be derived. You can find it uh, in the different book and on the internet, but over here we have to use that how this relation can be used to find the radius of curvature of such irregular shape, right? So so we can say that uh, in comparison with the rectangular coordinate system, we would have some reference axis or some origin, and with respect to that origin we will calculate the position and the velocity, right? But in the normal and tangential coordinate system, uh, it is fixed on our particle, right? As our particle moves, the anti coordinates is stuck with this particle, and our coordinate system will move with this with the motion of this particle, right? So therefore we can say that it moves with our particle, right? So I think this is a time where we should uh, see the important points regarding the normal and tangential, working with the normal and tangential coordinate system. So these are some important points you must keep in your mind to while solving the curvilinear problem related to normal and tangential coordinate system. So number one is that the anti-coordinate system are fixed on the particle. That is why the coordinates move with our particle. Rather, in a rectangular coordinate system, our origin and coordinate and references are fixed. Similarly, we have only one component of the velocity in normal tangential direction, which is the tangential component only, right? Now, AT is actually the change in its speed, where the normal component of the acceleration is due to the change in its direction, right? For suppose if I can say that if I have a straight line, right? So can I say that this straight line is actually the arc of a circle having an infinite radius, right? So the straight line is actually the part of a circle having an infinite radius. As I have said that normal component of the acceleration is equals to v square by rho. So if this rho approaches to infinity, then the whole become the zero. That is why we have only one component of the acceleration, which is at in the rectilinear uh, uh, analysis. So that is why we can say that uh, along the tangential direction, which is actually at is equals to dv by dt, and it is actually the rate of change and its speed. That is why we can use all the relations which we have studied in rectilinear kinematics. So like ads is equals to vdv, and all these relation which we have studied as a constant acceleration, so all relation can be used while calculating the acceleration in the tangential direction. Finally, an, which is actually small an, is the centripetal acceleration, which is always points toward the concave side of the path, right? And if the path function is known, then the radius of curvature can be calculated, as I have said you, that 1 plus dy by dx square by half, and this can whole be divided by d square y by dx square, right? So this is the equation for calculating the radius of curvature at any point whose function is given to you. So these are some important points which you should keep in your mind while calculating the acceleration, velocity, or the position in the normal and tangential coordinate system. So as we studied that in rectangular coordinate system, if the curve is in space, then it will be represented by the x, y, and z axis. Similarly, in normal and tangential coordinate system, we have studied normal axis and tangential axis if the curve is in a 2D. But if the curve is in space, then it will be defined by using three axes. Number one is the tangential axis, number two is the normal axis, and the third one will be the binomial axis, which is represented binomial axis, which is represented by the b. So here you can see that this is the curve which is in space. So a position of the particle or its velocity and the acceleration can be defined in these three coordinate axes. So let's start some problem and see how these concepts can be applied. So we are starting problem 12-115 of your RC Hibbeler 14th edition, and in this problem you have a car which is originally at rest, and it will gain the acceleration of 0.05 t square, and we have to determine the magnitude of its velocity and acceleration after 18 seconds. So by seeing this problem, you can easily say that the car is moving in a straight road, then uh, after it will move to this curved path, right? So as far as if it is moving on this straight road, it will have only one component of the acceleration. But if it moves to that curved path, then it will have two components of the acceleration. One which is tangential, and the other one is the normal acceleration. So first of all, in order to solve this problem, we have to see that after 18 seconds, will cover the distance above 300 feet or below this. So if it remain in this straight line, then it will only have one component of the acceleration, otherwise it will have the two. So in order first to solve this problem or to calculate the velocity and acceleration, we should calculate the distance, that what will be the distance after the 18 seconds. So, and similarly, as it is moving in a straight line, that is why we can say that this acceleration is a tangential acceleration, because the straight line represents the arc of a circle having an infinite radius. So that is why it is only have one component of the acceleration, which is tangential acceleration, and normally in normal and tangential coordinate system, tangential acceleration is provided to you. So let's start solving the problem. So we have given the acceleration, which is a is equals to at is equals to 0.05 t square, right? And we know that uh, velocity acceleration is actually dv by dt. That is why this velocity is a dt, and we are starting from 0 to v. That is why we are having these limits. So we have acceleration which is 0.05 t square. So when you integrate it, you will get v is equals to 0.016 t cube. So this is the function of the velocity. This is the velocity which is actually the function of the time. Now let's calculate the distance, and after that we will apply the limit. Mm, Now we know that v is equals to ds over dt. That is why ds will be v dt, right? This is your kinematics relation, and this is 0 to s and 0 to t, and we have calculated v as 0.016 t cube, right? So when you solve this equation, you will get s is equals to 4.1 exponential minus 3 t4, right? So as the time is given to us, that is why when t is equals to 18 seconds and you put values in the equation, you will get velocity will be 93.3 feet per second, right? And you will get the s, uh, which is 430.4 feet, right? So the our s is 430, which is actually greater than this 3 feet. It's mean our car is in this curved region, okay? And when our body or a particle uh, is in curved path, then its acceleration will have two component. One is along x, one is along the normal, and the other one is along the tangential direction. So we will calculate the tangential acceleration, which is actually at, and which was provided to you, and it is actually 0.05 t square. So you will just put the value of t, and you will get 16.2 feet per second square, right? And the normal acceleration will be v square by rho, and you have calculated velocity, which is 93.3 square over rho, which is 240, right? And when you solve it, you will get 36.2 feet per second square, okay? And after that, you will calculate the resultant as a is equals to at square plus an square, and when you put value, you will get 339.65 feet per second square. So that is how you have calculated your velocity and acceleration after the 18 seconds. So this is the procedure by which you can also solve the curvilinear problem by using normal and tangential coordinate system.